Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In today's lecture, we will start by discussing about the optical activity of organic molecules. As you know that light possesses the properties which is best understood by considering it to be a wave phenomena in which the vibrations occur in right angles to the direction in which the light travels. So, if a light is traveling in this direction towards you, then the electric vectors are vibrating in the horizontal plane and the magnetic vectors are vibrating in the vertical plane. And there are infinite number of such planes in which the electric vectors and magnetic vectors are vibrating at a perpendicular direction. So, each of these possible orientations are orientations of the electric and magnetic vibrations. So, when we have a source of light, what we have is a straight light where the electric vectors, suppose these, and the magnetic vectors are vibrating in perpendicular direction, and those vibrations are possible in all possible directions. So, when we pass this light through a polarizing filter, what happens is then it only allows the one part of the light, the electric vector of the light, to pass through, and this gets polarized in one particular plane. So, this is called the plane polarized light, and this plane polarized light, when it is passed through a solution of a chiral compound, what is observed is that the plane of polarization is rotated. Vibration was happening in this direction, and now the vibration is happening in a different direction, and there is a specific angle between the two directions called alpha, and as an observer you can see this particular diversion. So, based on this we can identify whether an optically active compound is rotating the light in the clockwise direction or in anti-clockwise direction. A plane polarized light is a light whose vibrations takes place in only one possible directions or one possible planes. Ordinary light is turned into plane polarized light by passing it through a prism made up of a material known as Polaroid, or more traditionally through a piece of calcite, a crystalline form of calcium carbonate, so arranged as to constitute a Nicol prism. And an optically active substance is one that rotates the plane of a plane polarized light. If the rotation of this plane is in the clockwise direction, then the substance is said to be dextrorotatory, and if it is counterclockwise, then the substance is said to be levorotatory. That means, if the plane of the incident radiation was in this direction and the rotated plane is in this direction, it rotates in the clockwise direction by angle alpha. This is called the dextrorotatory sample, and in case if the plane was in this direction before passing through the sample and then it rotates the plane in anti-clockwise direction, then we call it as a levorotatory sample. So, this is termed as a plus and this is termed as a minus rotation by convention. The optical activity of a compound is determined by an instrument called polarimeter. You have seen the schematic diagram in the previous slide. So, when we have an optically active compound, but an equimolar mixture of two enantiomers is called a racemic form, or either a racemate or a racemic mixture, which essentially means that you have both the enantiomers present in 1:1 ratio, giving rise to 0 optical rotation. So, it does not show any optical rotation of the plane polarized light, and that is why it is designated as a plus minus compound. Similarly, racemic forms and enantiomeric excess we need to understand. A sample of an optically active substance that contains a single pure enantiomer is said to be enantiomerically pure, and optical activity of that particular compound identifies the specific rotation of that particular substance. So, when we calculate enantiomeric excess, it is defined as the moles of one enantiomer minus moles of the other enantiomer multiplied by 100 divided by the total number of both the enantiomers that is present. So, that can be calculated from the optical rotation as observed specific rotation divided by the specific rotation of the pure enantiomer multiplied by 100. So, here I have introduced a term called specific rotation, which is written in square bracket with the sign alpha, and T and lambda are the two constants. Temperature is mentioned as T, normally 25 degrees centigrade, and lambda is the wavelength of the light that is used. In general, we use sodium vapor lamp. So, sodium D line wavelength is used for this measurement. This is nothing but equal to alpha, that is the optical rotation that is observed, divided by C into L, where C is the concentration of the solution and L is the path length. Path length of the polarimeter tube. This concentration C is measured in grams per ml unit, and this path length is measured in decimeter unit. So, this specific rotation is first measured for the pure enantiomer, and specific rotation of a mixture of two different enantiomer is measured accurately using a known concentration of the solution, and then one can calculate this percentage enantiomeric excess. So, let us see with one example. If the observed specific rotation of an enantiomeric solution is 6.76 degree and the specific rotation of the pure enantiomeric solution is 13.52 degree, then what is the enantiomeric excess percentage? So, use the previous formula that we have seen in the previous slide. 6.76 degree divided by 13.52 degree into 100, which gives you 50%. Now, the question is, what do we mean by this 50% enantiomeric excess? It means 50% of the mixture consists of plus enantiomer, that is the excess, and the other 50% consists of a racemic form, which is essentially plus minus. So, what does it mean? I have 50% of plus in excess plus 50% is a mixture of, rather 1:1 mixture of plus and minus, which essentially means 50% of plus from this part 25% plus and 25% of minus. So, overall this is 75% of the plus isomer and 25% of the minus isomer. So, this is how we should interpret the enantiomeric excess value that is sometimes written in the label of a compound which we may buy from a shop. Consider the second case. Consider that the S2-bromobutane has a specific rotation of plus 23.1 degree, and therefore, R will have minus 23.1 degree. It is obvious, and that is the optical activity of a mixture of R and S 2-bromoethane, whose specific rotation was found to be minus 9.2. So, we want to know what is the concentration ratio of this R and S. So, what we see that the negative sign here tells you that the R enantiomer is in excess or is dominant one, because R has negative optical rotation. That means it is rotating the plane in the anticlockwise direction. So, then we can calculate the optical purity as specific rotation of the mixture by specific rotation of pure sample. So, we can identify it as 100 into minus 9.2 divided by minus 23.1. Therefore, the calculation shows that this indicates a 40% excess of R over S. Hope you can follow this. So, now we move to next part of this course, where we will try to understand other different possible isomerisms. So, in that we need to learn what are epimers. Epimers are those compounds which contain more than one stereocenter, and those two compounds differ only at one stereocenter, while the stereochemistry of all other stereocenters are the same. Which means, if you have a compound and they have multiple stereocenters, except one, all stereocenters have the same R or S designation, and there is a difference about only one stereocenter. So, those compounds are called the epimers. So, here we have an example where we have alpha D glucopyranose and beta D glucopyranose. See, note this term D, which we will discuss in one of the future lectures. For the time being, you take it as a designation of the chiral center, which is designated here. So, now in this case, you see the chiral centers 1, 2, 3, 4, 5, all of them except one has the same stereo electronic stereo arrangement. Like this is in the equatorial plane, this is equatorial, this is also equatorial, this is equatorial, this one is also equatorial, this OH is equatorial, this OH is also equatorial. But when we look at the OH group at carbon number 1, here it is in the axial position and here it is in the equatorial position. So, these two isomers are termed as alpha and beta forms of D glucopyranose. So, these are called the epimers. Similarly, if I try to draw another molecule like this, and this molecule, where we have 3 chiral centers, but the chirality of this point is different in these two compounds. So, these are also called the epimers. Hope you can understand which compounds are called the epimers. So, when we have a set of different enantiomers in a solution, we call it as a racemic mixture, and sometimes we may need to isolate the 2 enantiomers from a given racemic mixture. So, an racemic acid can be treated with an optically active base to convert it into diastereomers. We have discussed about diastereomers a bit, and we will come back to these once again in the coming lectures. Diastereomers can then be separated by crystallization and distillation methods, and sometimes by their solubility as well. So, then we treat the individual diastereomers with a mild acid and get the separated enantiomers out as a plus and minus forms. Now, let us try to understand the isomerism in the allenes and biphenyl systems. What we know about allene? Allenes are those compounds which contain C double bond C in a row like this, and the two hydrogens on the other carbon are above and below the plane of projection. So, this contains two sigma planes. One sigma plane is the plane of projection, and the second sigma plane is the perpendicular plane to the plane of projection. So, this compound has, as you know, a C2 plus 2 perpendicular C2s. So, it gives you the point group D2, and then we have in the past seen that this molecule has the diagonal planes, rather sigma Ds. These sigmas are actually sigma Ds. So, we determined the point group as D2D. But then when we substitute these hydrogens, two of the hydrogens on carbon number 1 and 3 by some group, what we see that it gives rise to a chiral axis. So, suppose if we substitute one of the hydrogens on first carbon by methyl group and the other hydrogen on carbon number 3 by a methyl group. So, this gives rise to a chiral axis, which is the axis containing the 3 carbon atoms. So, when we try to draw the mirror image of this molecule, what we see is this one. What we now clearly see that these two molecules, that is molecule suppose say 1 and 2, they are non superimposable mirror images. So, they are pair of enantiomers. Which means we should be able to designate them by the nomenclature of R and S. So, let us try to see how those RS can be done in the next slide. Now, suppose we take the molecule like this with two groups having substitutions A and B, and on that also I have A and B. Remember, A is methyl and B is hydrogen. For my simple understanding, I am converting it into A and B. So, now this molecule has to be converted into the wedge projection first to make it Fisher projection. Suppose I am looking at this molecule from this side. So, what do I see? I see that the molecule has this A and B pointing upwards with respect to the front carbon, and it is on the right and left hand side of the observer. So, on the right hand side of the observer you have the group A, on the left hand side of the observer you have the group B. When you look at this carbon from the right hand side, this A and B will appear above and below, but both are pointing away or behind the carbon on which it is connected. So, we draw those two carbons as the points which are below. Now, the question is how we determine the priority. So, the priority is determined based on the front carbon first and then the back carbon, and on the front carbon methyl is higher priority over hydrogen. So, the priority here is 1 and 2, and on the back carbon the priorities are 3 and 4. I have the priority identified here as 1, 2, 3 and 4. Now, if you look at this wedge projection, it is depicting the method of Fisher projection in which you should draw a Fisher projection. So, we can straight away convert it into a Fisher projection. In Fisher projection, the bonds which are in the vertical line are below the plane of projection, and the bonds which are in the horizontal line are above the plane of projection. Therefore, we can straight away draw the projection like this, with the priorities identified. So, what we see here, we should go from 1 to 2 to 3. It is clockwise rotation, that is right. So, this is the R isomer of the compound. Now, let us try to see what happens if we look at this molecule from the left hand side. I have taken a different color for your easy understanding. So, when we are looking at this molecule from the left hand side, my first carbon turns out to be this and third carbon turns out to be that, whereas in case of the previous figure we have taken that as 1 and that as 3. So, now when we are looking at this molecule from the left hand side, what we have is A and B which are pointing towards me like this. So, these two groups which are in front of me pointing towards me above the plane of projection. So, those two groups should come like that, and the two groups which are on the back carbon are pointing like this, and on the right I have B and on the left I have A. Sorry, on the right I have B and on the left you have A. Now, what about the priority? Once again, now the priority will be on the first carbon. So, the groups on the first carbon will get the priority, higher priority 1 and 2, and the carbons, the groups on the back carbon will get priority 3 and 4. So, this 1 and 2 comes here, and 3 and 4 comes in the horizontal line. Now, you see here this particular projection is not in the way a Fisher projection should be drawn. So, what we should draw is we should rotate the molecule in plane by 90 degree and come to this projection where I have group A number 3 at the top, group B at the bottom, which is 4, and the group which was A at the top comes to the right hand side as number 1, and the group at the bottom, which was number 2, comes to the left as 2. So, now this orientation where the vertical line contains bonds which are below the plane of projection and the horizontal line contains the bonds which are above the plane of projection. So, it can be converted into a Fisher projection like this. Now, you see the priorities are again as it was before. So, now again 1 to 2 to 3 is clockwise rotation, and this clockwise rotation means the right hand side rotation. So, this isomer is the odd isomer. So, what we can see that a particular molecule looked at from either side turns out to be the same absolute configuration. Therefore, this molecule is the odd isomer 1,3 dimethyl allene. So, if we take the molecule which is the other enantiomer, we will try to find out what would be the S isomer in the following class.